No, I think everybody's counted for. Okay. All right. It is time. We have played around in finite dimensional vector spaces plenty long enough, and it is now time to go to infinity. And this will land us in the wonderful world of Hilbert space, wherein there lives many special functions which you have seen and played with in various contexts. Okay? So I'm going to start with a very precise definition of Hilbert space. This will be rather technical, and then we'll look at some of its properties. So I'm going to go slow with you to begin with, and then we'll pick up the pace a bit after we've gotten all the formal stuff down. So getting started, we need two definitions. The first one will seem almost obvious. A closed interval, A, B, is the set of all points x, where x is greater than or equal to A or less than or equal to B. And you are aware probably that open just uses the inequalities. It doesn't have, or sorry, it just uses the greater than or less than signs, not the inequality signs. Okay? So that's our first definition, and we're going to use a closed interval for lots of stuff. Second, a function is square integrable, which I will refer to as SI frequently and all over the place, on an interval AB if the integral from A to B of f of x squared dx, which is, of course, the integral from A to B of f star f dx, exists and is finite. Okay? So really basic definitions. Now, I want you to recall, I'm going to scratch the board, the definition of a vector space over a field F So the definition of a vector space is, of course, that we have a set of vectors over a field F. And the first and one of the most important aspects of a vector space is that if you the set of vectors with addition among them forms an abelian group with the identity equals 0. And then there's a lot of algebraic properties that scalars in the field times vectors satisfied. Okay, I'm not going to worry about these so much. All right, now we are going to consider the following. Consider the function space that is the set of all square integrable functions. Of a real variable x on a closed interval. AB. It does form a vector space. Now, you might remember that when I was showing you properties of vector spaces, I kept hitting on this example of polynomials of degree n. Okay, polynomials of degree n is a set of functions, but we showed that they actually correspond to and form a vector space, and then they have matrix realizations. Yes?
Just out of curiosity, you bracketed this in green. Is that not something we needed to like prove that function space or whatever is a vector space?
Oh, no. Yeah. We're going to talk about that in just a minute. We're going to talk about proving that it's a, I mean, this is just a definition, and this just happens to be, I mean, I can put that in red, but it's almost obvious.
Okay.
But okay, fine. And this red is housed in this green, so it's a theorem that's part of the definition. No, I'm just kidding. Okay. All right. So hopefully, obviously, the operations on functions are pretty obvious. So for example, if I take the sum of two vectors, okay, then that's just defined as the sum of the individual functions. Okay? And if I take a scalar times a vector, then that's just equal to the scalar times the vector as a function. Okay? Not equal to alpha f of x equals f of alpha x. Okay? I mean, this is maybe a construction that you could play around with, but it's definitely not what we mean. Okay, so for example, if my function was ax squared plus bx, then you might think alpha f is a alpha x squared plus b alpha x. But I'm saying no, alpha f is alpha a x squared plus alpha b x. Okay, I mean, it's almost obvious. You wouldn't think otherwise, but I just want to lay this down.
What does like the bracketed alpha f even mean though?
What is the...
Like that's not a associativity thing, or yeah, that's just like you're defining a function alpha
Well,
f.
this is a function itself.
Okay. Okay.
Now this is a scalar times a function.
Okay.
Okay. You good?
Sure.
I mean, remember, part of the story here is that if you take a vector and you multiply it by a scalar, you get back a vector.
Yeah.
And this is just calling this entire thing a function.
Okay.
Okay? Whereas here it's a scalar times a function, which obviously is still a function. It's almost that definitive.
What would you call f by itself then?
A function.
So if alpha, oh, I see, okay, yeah.
So we could call this g of x, and we're just saying that alpha times f gives me another function, g, which just happens to be equal to alpha times f. Okay, we good? Well, it's about to get hairy, so if this is not clear at all, just let me know. We good, folks? Online?
Good.
Oh, one of you said good. Okay, good. All right. Scott.
Yeah.
You are going to tell me what is the one thing in the definition of our function space and the recognition of it as a vector space, what's the one thing we need to check? I'll give you a hint. It's here.
It's a abelian group, or that
It's an abelian group, and in order to be an abelian group, you have to satisfy the
like associative
yes and
span of space.
Kind of, but that's not the language we used in groups. You're getting there. So what other properties define groups?
I'm just gonna avoid that.
Help them out, folks. Help them out.
Commutative?
That's
No. Well, this is commutative.
That's
Okay.
what abelian is, right?
That's what abelian means. But what other properties define groups?
the operator.
Closure has to be closed.
Yes.
I heard it. Closure.
Oh,
If I take two elements of the group and I combine them with the operation, I must give me back another element of the group. Now think about it for a moment. The space is the space of square integrable functions. So the question is, if I take two square integrable functions and I add them together, am I guaranteed that their sum is square integrable?
Yeah.
Yeah?
Feels
Oh,
like it's
yeah,
just
we
like
had
a
to
linear
prove that, though.
combination.
We're going to prove it.
Yeah.
Thank you. We're going to prove it. Okay? It's really the only aspect of this that we need to prove. So is square integrable plus square integrable equal to square integrable? I love that. Isn't that an awesome equation? It's cool. Anyway, okay, here we go. So consider,
It is reverse.
huh?
The is particularly funny on the front.
Oh, thank you. Thank you. Thank you.
I
Okay, here we go. So consider the sum of two functions, and let's find the square of their magnitude. So we know that this is f1 star plus f2 star times f1 plus f2. Okay? Now this is the set of all square integrable functions, and that means that the functions can be complex valued. They are only a function of a real variable x, but the functions in coefficient land, or whatever land, function land, can have complex quantities. So when we're doing things like this, we have to start. Yes?
Have we defined them as being orthonormal?
We haven't even talked about that yet. I haven't even introduced an inner product yet.
Okay.
Okay? I will in just a minute, but I gotta do this proof first, okay? So here we go. We can bang these out. This is just the magnitude squared of f1, because I'm doing f1 star times f1. The magnitude squared of f2, because I'm doing f2 star plus f2. And then I have f1 star f2 plus f2 star f1, which I actually don't know that about that. Okay, that's just expanding out that binomial. Now here we go. This is f1 squared plus f2 squared plus twice the real part of f1 star f2. How many people buy it? Raise your hand. How many people are kind of like, I don't know if that's true.
Does it have to be f1 star f2? Could it not have been the other way?
Yes,
Does it matter?
it doesn't matter.
Why is there no complex part?
Okay, I was debating whether or not to show you this, but I'm going to show you. Here we go. So let's just imagine for a moment, I'll just do it here and then erase it. F2 or F1 is A plus IB and F2 is C plus ID. Okay, they're just complex value things. Then what we have is A minus IB, C plus ID, plus A plus IB times C minus ID. Okay, F1 is A plus IB. This is, of course, F1 start. Sorry, I'm pointing here. Okay, we on board? Right? Now all we have to do is multiply that out, and we're going to get AC plus BD minus IBC plus IAD plus AC plus BD plus IBC minus IAD. Ooh.
I mean, it just kind of makes sense looking back to the original function. It better all be real. But
Yeah. Okay? Everybody on board? Okay. Now, we can argue that this guy is actually less than or equal to this guy. Okay? Because this guy is going to be this plus a piece, plus a piece, plus a positive piece. So that means if I let that piece come back into the story, this thing is less than this. We on board? Okay? And now what we can say is the following. First of all, this is equal to F1 squared plus F2 squared plus 2F1 F2. Okay? It might not be obvious, but these two are the same. Everybody on board with that? Or does anybody want to see it? We good?
Yeah, I can see it.
Okay. Yeah, you literally just, you just take a sample function, A plus IB, C plus ID, do this, compare, and you'll have exactly the same thing. Okay? All right, now, we've got a but. Sorry,
Real mature.
I know, it's that kind of day. All right. So if I consider the difference and the square of the difference, then I have F1 squared plus F2 squared minus 2 times F1, F2. All right? Well, this is greater than or equal to 0. Zan, I know you're there.
Like you call my card all the time. Huge bummer.
Why is this necessarily greater than or equal to 0?
Well, that part squared is bigger than the other side.
Yeah, so these are real, right?
Yeah.
And then you're squaring something that's real, so it's obviously going to be positive. And then this is equal to the right, so the right-hand side is greater than or equal to 0. Good job. Excellent job. Strong work. Strong work. All right, here we go. Ready? This implies that F1 squared plus F2 squared is greater than or equal to 2F1 F2, right? Good. So now we have the following. F1 plus F2, quantity squared, is less than or equal to 2F1 squared plus 2F2 squared. Everybody see that?
Yeah.
Remember, it's smaller than this. Okay? Now then this implies, that the integral from a to b of f1 plus f2 squared dx is less than or equal to twice the integral from a to b of f1 squared dx plus twice the integral from a to b of f2 squared dx. Right, if this is less than this, and I just integrate this from a to b, integrate that from a to b, it doesn't change the direction of the inequality. Can anybody tell me an interesting, useful property of this integral?
It's a square.
It's a square integrable function.
Okay, yeah.
Yeah, so this is, it's what? It's SI, but that means that this integral is finite. This integral is, therefore this integral is the sum of,
Less than finite.
it's
Less than finite.
it's less than finite, thank you. So what we've just proven is that the sum of two functions, the sum of two square integrable functions is itself square integrable. That is, this is closure, which is one of the key elements in demonstrating that you have a group. Okay? We all on board? Good. All right. So now we're going to, I'm just going to erase this. Now we're going to introduce the inner product. And we are going to bump into one of the first really and truthful subtleties in this entire story. And you know, after you've provided a proof, can you turn the red into green?
No.
Damn. Did you guys go out the other night and play? Anyway, I'm just kidding.
What was that question?
I don't know. I just wanted it all to be green inside of a definition
go
box.
out?
It doesn't matter. I'm just screwing with you guys.
I mean, sure.
Yeah. Okay. All right. Okay. So I'm going to define an inner product. Yes. I love it. Okay. So an inner product has. So this can be in a real or a complex vector space. It's a scalar valued function. So you take the inner product of two vectors and it gives you a scalar in the field over which the vector space is introduced. And it has three important properties which go into defining it. Okay? This is an abbreviated version of our definition of the inner product. And I even showed you back in the land of finite dimensional spaces and vector spaces and so forth that there's different versions of the inner product. Okay? You're used to the sort of matrix related one, where you turn one of them into a row vector and keep the other on a column vector. You star everything in the row vector and then you just do matrix multiplication. But there's other ones. Okay? All right, so we are going to use the following inner product. If I have two functions, the inner product of the two functions is the integral from A to B of f1 star x f2 of x dx. Okay? So on our space of square integrable functions, we will be interested in this inner product. Okay? Now, we will generalize this a little bit. I'll talk about that in a bit. Okay? But, well, let's see. Okay, so first of all, realize that the definition of square integrable is already using the inner product of a vector with itself, or of a function with itself. Okay? So we can go ahead and define the magnitude of a function as the square root of the inner product of the vector with itself. So this is the norm. And now what we can show is that the inner product of two different functions always exists and is finite. So consider f1 star f2 magnitude. We proved earlier that this is equal to f1, or the magnitude of f1 times the magnitude of f2, which we also argued was less than 1/2 the magnitude of f1 squared plus the magnitude of f2 squared. Okay? So we can take this and we can integrate both sides.
You mean one of those f1s be an f2 on the left?
Sorry, say that again? Oh, yeah, sorry. Well, they're twins, so it really doesn't matter if you call it 1 or 2. No, I'm just kidding, they're not twins. They're not twins. Okay? This is less than 1/2 the magnitude of f1 squared plus the magnitude of f2 squared. Okay? And this is, of course, less than infinity because these are square integrable. All right? So what we've just shown is that the inner product of two functions, which is just the integral from a to b of f1 star f2 dx, exists and is finite. Okay? Now, I don't know if that's obvious. We have this space of square integrable functions, so the norm of each vector is finite. We proved that the sum of two functions is also square integrable. That's closure of the group. Now what we've just proved is you can take any two functions you want and add them to, or multiply them together with the inner product, and the result of that is also finite. Okay? So the inner product, obviously, the inner product here on functions obviously satisfies these, except for one of them. Andrew, which one of these three properties do you think we need to be careful in assuming that the functions on this space will satisfy? Three. Which part of 3? Well, there's 2 parts.
Yeah. That one? No, that one.
Yeah, that one. Yeah, it turns out that the satisfaction of this is a little, we have to dig a little bit. So let's dig a little bit. And this is going to take us down a path. So, does the inner product of f with itself equaling 0 imply that the function equals 0 for all x. Josh,
That's me!
get up here.
No,
Oh, he's way back on top of the deck.
He was on his phone. I got
I
him.
was.
Why am I so-
Okay,
Got an email.
answer that question.
Just answer it. Write down yes or no.
Answer the question. Answer the question.
Yes.
Okay, go sit down.
Thank you.
Good job.
You got it? Yeah. In most cases, yes, but it turns out not quite. Okay? And again, this is going to take us down an avenue which maybe you've heard of and know about, maybe you don't. I want you to consider the following function. And I will probably go up here. Now, f, the inner product of f with itself is 0 means that f is 0. This involves an integral. Makes sense. So consider the following function. And this is called the Riesz-Fischer function.
Why are these people's names always so complicated?
It looks
Hard to
French.
spell.
The French don't know how to spell it.
Okay? So the Riesz-Fischer function is equal to 1 if the argument x is a rational number, and it's equal to 0 if x is an irrational number.
What does a graph of that look like?
That's a very interesting question. Okay? So, first of all, if you graphed it, it would be kind of boring, right? Because,
Wouldn't it just look like two
But like-
lines?
okay, so we got 0 and we've got 1. And we're going to define this, hold on, pause. We're just going to define it over the interval from 0 to 1. Excuse me. Okay, so 1/2. What's the value? 1.
You're gonna graph it like ones.
What's the value at 1? 1. What's the value at 3/4? 1. What's the value of pi?
That's not on there.
Yeah, no, it's not on there, but 1 over pi.
You can say 1 over root 2 if
I
it's.
just said
Pi over
1 over
4.
pi.
1 over pi is 0.
1 over pi is 0. The square root of 2.
Or is that on there?
That's gonna be the 0.
Or 1 over the square root of 2. I don't know. It doesn't matter to me.
Like, it's gotta be like.
No. It's going to be a lot of points.
Okay.
Yeah,
It's gonna be.
But are they connected?
Points, isn't it?
No.
because you can always get like an irrational number between two.
Yes,
rational
thank you.
numbers.
Between any two rational numbers, there are irrational numbers. Okay?
Is that the same the other one too?
Say it again.
Between any two irrational numbers, there's a rational number? Is that all?
Sure. Yeah. No. Oh, no.
Well, maybe
No.
necessarily.
No.
Well, between pi and 1 over pi.
Just
and 1 over
wait a
square
minute.
root
Wait till you see where this story is going to go.
Okay.
Okay. You went away. We're going dots.
Okay.
Cool. All right.
Thanks for catching me.
You really
So,
just-
So the question I would now like to ask is, what is the inner product of the square root of b with itself?
What?
Long square.
What is the square root of
It's the
this?
square root of this function.
Is that
What
just
is
the
that
same
line?
exact
Just-
thing? Wouldn't that just be the
You'll-
same function?
Let's shut up for a second. With a equals 0 and b equals 1 in the definition of the inner product. Okay, the inner product is defined over an interval. Our interval happens to be defined from 0 to 1, so that's going to be the limits of the integral defining the inner product. Okay? Now, First of all, you know, this is obviously the integral from 0 to 1 of the square root of d star times the square root of d dx. But this is a real valued function, so d star is just going to be d. So this just gives you integral from 0 to 1 of d dx. That's why I chose the square root. Okay? You happy? I just wanted a goddamn single integral of d. That's it.
How the hell do you integrate this function?
I know. Let's try it. Okay? We are going to kick it old school. Okay? Because after all, the integral was given a definition back in the 1800s. They summed rectangles. Let's sum rectangles. Okay? So a very quick reminder. No. Listen, this is cool. Okay? And I'm going to do this with a curve, and then we'll apply it to that story. So if I have some curve, okay, and I want to do the integral from 0 to 1 of that curve, then we realize that the definition of the integral is the area under the curve. Okay, that's the fundamental definition, and then through the fundamental theorem of calculus, you relate that to the antiderivative. Okay, but the definition of the integral is just the area under the curve. And I'm going to only play with positive curves. The negative part you can just extend this discussion to, but we're not going to worry about that because this is a positive function. This is a positive function. We don't have to worry about the negative part. Okay, so you guys know how to do this. If I pick a little interval dxi, then I can consider two rectangles. All right, one of which, and this is going to be, this is the value xi, and then this is dxi. So the value here is just xi plus dxi, okay? And we have two different rectangles that we can use to sum to find the area under this thing. We can use the one here, the green one, which sits below the graph, and actually intersects the graph at the minimum of fx over the interval dxi. So the minimum value of the function over this interval is this corner right here. We can also use this larger triangle, which actually intersects with the maximum. Okay? You can use either one. And then the integral from 0 to 1 of f of x dx is the limit as dxi goes to 0 of the sum over I of the area of the rectangles, which is dxi times f of xi, where this guy can be the maximum value of f of xi, or it can be the min. Okay? I mean, the function is not constant over the dx interval, so you got to pick a value. Okay? Normally, it doesn't matter which you choose, and in fact, in order for the Riemann integral to exist, these have to give you the same answer. Okay? So max and min have to give you the same answer if you want to argue that this integral defined in this way actually exists. Because otherwise, if they don't give you the same answer, which one do you use? Or is there two answers to the what is this integral? No, there's only got to be one answer. And if you've got these two different methods to approach it, they have to give you the same result. Okay? And this is true. This happens for pretty much everything that you've ever integrated. Except for this. Let's think about this for a moment. So if I take an interval dx, that interval, if if it is small enough, we'll have exactly one non-zero point in it. And we're taking the limit that dxi goes to 0, okay? So, if I define the integral, and we'll just call this the Dirichlet function, if I define the integral of the Dirichlet function as the limit as dxi goes to 0 of the sum over I of dxi, we have two possibilities. We can either take the width of this rectangle and multiply it by the maximum, which is 1, or by 0, which is the min. Well, if you do this integral, are these two going to agree? No, they're not. One of them will give you 1, and one of them will give you 0. Is this thing Riemann integrable? No. Is it an element of this space? Well, didn't I define square integrable as integrable functions? I mean, I define square integrable in terms of an integral. What do you think?
It's not square integrable then.
So this is not square integrable, huh?
So it's not part of the space. So we don't need to worry about it?
Well, this is not the only function that's like this. It turns out there are many that are like this.
But then aren't they just not included? So we don't have to worry about it?
Well, then the question is the space complete? Which we'll talk about in due time, but is the space complete? That is, if I take two vectors in the space and I add, or two elements of the space and I add them together, if the sum of two elements gave me this Dirichlet function, but the Dirichlet function is not in the space, then the space is not complete.
But is there any two functions you can sum that would give you that?
Not two, but more than two. But you can sum as many as you want.
Huh.
Don't worry about it. It's going to turn out that we're going to include this in the space.
Okay.
How?
Different type of integral?
I was gonna say that.
A different type of integral. Yes, that is exactly the right answer. So, how many of you have ever heard of Lebesgue? All right. We are going to introduce a new integral, okay, called the Lebesgue integral. And the Lebesgue integral will give us a definitive answer to what is the integral of this. And it will also give us the definitive answers to what are all the Riemann integrals, because it turns out that any Riemann integral is also a well-defined Lebesgue integral, but the set of Lebesgue integrals includes things that are not Riemann integrable, like the Dirichlet function. Integrable. Integrable. Okay, here we go. So I'm going to define a Lebesgue integral for you, and then we'll see how it cures that. Here we go. And what's beautiful about the Lebesgue integral is that it literally, it's like, yeah, why couldn't you do that? Shit, it's so easy.
Yeah.
Huh?
You spelled
They
that?
spelled an A.
Oh, sorry.
Silence. Oh, of course.
Oh my
That's
God.
of course.
I've had that.
How else did you spell it?
Sorry. That's Lebesgue. Anyway.
Bad
My bad, dude. My bad, sorry. Sorry!
Time for French mockery.
Okay, here we go. Now, I've got a function over some interval, and maybe I just want to integrate to 1 or something like that. Here's what we're going to do. We're going to take this picture, And we're gonna go, everybody do it, ready, on 3, 1, 2, 3. You are totally not paying attention. I need you to do it right now. Thank you. Okay, no, in all seriousness, what we're gonna do is instead of considering summing over these vertical rectangles, where by vertical I mean its longest length is in the vertical direction, we're gonna sum over horizontal rectangles.
Sure.
Thank you.
I'll get you the area, why not?
Okay?
But are,
Hold on. Just chill, chill. Okay, now, what we're gonna do is in this space, we're going to consider this is obviously the f of x axis, but we're also going to treat this as the t-axis, and then we're going to define the upper part of this rectangle as t, and the lower part of it as t minus dt. Okay? And then I want you to notice something. Here, f of x is greater than t. The values of the function are greater than the value of t. Whereas over here, f of x is less than t. I mean, that's the t. And then similarly here, the function is less than t. Okay? Now, what we can do is we can calculate the area of each of these strips in terms of dt times something we're going to call mu x f of x greater than t, where this mu simply calculates for us the width of the region which is less than, or sorry, which is greater than t. So the width of the rectangle, this is in the dt regime, the width of the rectangle which is sitting under the curve.
because you have sort of two edges there, so like min or max, or is that what we're about to do?
No, we're not even going to do that.
Okay.
Not necessary.
Okay? And of course, what's nice about this, and where it becomes interesting, is this thing goes across the entirety of the graph, so it picks up all of these widths. Okay? Whereas for a function, you have one rectangle per dx. Here for a dt, I can pick up many of these, especially if it's an oscillatory function. Yes?
What if you have like a y equals x? How would you draw a rectangle like from function to other part of function? If it never comes back down.
If it never comes back down?
Yeah.
Sorry, ask the question again?
So like for like a f of x equals x, where it just goes on,
Yeah.
and it never really comes back down, so how would you define a rectangle
Yeah.
under it?
Well, you're going to have an interval,
Mm.
and so that, in that case, your rectangle would start on the curve, and then it would just go to the end of the interval.
Okay.
Yeah. Okay? Now, if you think about this function mu, then if we integrate from 0 to infinity mu x f of x greater than t dt, okay, so now I'm integrating over dt, which means I'm adding up all of the contributions from these dt elements. They're all here non-zero if they're underneath the curve, and if they get above the curve, they're zero. This thing is non-zero if it's below the curve. Okay? So if I integrate this thing over dt, what is that equal to? I'm literally,
I mean, it should be just the integral of the function.
yeah, that should be the integral from a to b, f of x dx. Okay? Now, mu, this thing here, defines a measure of integration. Okay? You might or might not have heard of the word measure talked about in your calculus class, but in this case it's just dx. But the measure can be many different things, especially in multidimensional integrals. Okay? So this defines a measure of integration here. So that means that we can introduce the following notation, that the integral over the interval from a to b of f of x dx is equal to the integral over the interval from a to b of f d mu. Okay? Where this integral is defined in this way.
What is the, like, why is the interval like a comma b at the bottom now? Is it like we have to, it's like a u sub where we have to like plug in and figure out the actual
Yeah.
limits of a type
Yeah.
thing? Okay.
You're not integrating over dx.
Yeah.
Okay? So, as promised, anytime this integral is well defined, so too is this one, through this chain of definition. However, there are cases where this thing exists and this doesn't. For example here, if we consider the integral of the Riesz-Fischer function, then what we have is the following. If I pick a point on this function, and I take t minus dt, so where is the mu non-zero?
Mu is always 0 for that function.
Well, no, it's non-zero right here, because it's underneath the non-zero value of the function.
But it's just a single point, isn't it?
Exactly.
So it's basically infinite.
We're calculating the area of this thing. We're calculating its width times its height. And the area is 0. Okay? Now, you might look at that and go, oh, damn it. The Riemann gave me a 0. But the Riemann also gave you 1. And there was no preference on which of those would be correct. They should have been the same damn value. The Lebesgue integral of the Riesz-Fischer function is 0, period. No argument about it. Okay? So, what we find is that the integrability, which goes into the definition of square integrability, if we use the Lebesgue measure, we enhance the space of functions. The good thing is, we will never have to deal with Lebesgue integrals specifically. All the examples and functions we'll work with, you could just use the Riemann, the more familiar integral context. But all of our definitions will hang on the Lebesgue integral, okay? Because it covers more functions. Now, the Lebesgue integral is actually quite nice for a couple of reasons. One of which is if I consider the limit as u goes to 0 of the integral over t of a function of t and u, I can actually freely interchange the limit and the integral if I'm working with a Lebesgue measure. You're not always guaranteed that in a Riemann integral.
That feels like something with very limited usefulness.
Say it again?
That feels like something with very limited usefulness. Like, I don't think I've ever dealt with a limit and an integral.
Well, wait until I talk what I'm going to talk about for the next couple of lectures.
Okay.
Okay? All right, so, wait a minute. Hold on. So, how does this address this?
Just disproves it.
Huh?
Just disproves it.
Well, it seems like it did. It said if the inner product of f with itself, a function's inner product with itself, is 0, which the square root of d has an inner product with itself, which is 0, then f of x equals 0, but d of x doesn't equal 0 everywhere.
So you disproved it.
We just screwed this up.
We need to redefine our inner product.
No,
Oh, okay.
we need to redefine,
Redefine that. No.
we need to redefine
Zero.
0.
Oh, God.
Okay? No. I mean, we're getting there. We're getting there. So our statement is going to be
Take 0 from
That's not almost zero.
almost 0 everywhere. Okay?
What does that mean?
Also, how is the Dirichlet almost zero?
No, you don't.
So the Dirichlet is almost 0. So the Dirichlet function, and any other function like it, is almost 0 because the measure is 0.
Okay.
So if you have a function whose measure is 0, then that function is non-zero, but it is almost 0, in the sense that if you integrate it, you're going to get 0. And I'm not talking about due to positive and negative cancellations. It's a purely positive function. But if you integrate it, you'll get 0, even though it's non-zero. This is the definition of an almost 0 function.
Is that because it's not,
Well, I mean,
it's discrete, and so you can't really add everything up?
well, that was part of this argument.
Yeah.
Because every one of these rational numbers is isolated.
Right.
When you actually do the horizontal rectangle, the width of that is always going to be 0.
So that's why some area is nonsense.
Yes. Well, it's not nonsense, it's 0.
Yeah, well, yeah.
And the integral is the sum over all of these zeros.
You missed the part where we said the rectangle was
Oh.
Okay? All right, so again, we're going to utilize the Lebesgue integral in our definition, but we're never going to have to actually work with it. Okay? Because all the functions we're going to work with will be square integrable according to the Riemann sense of integration. But it's important because otherwise this space might not be closed. Okay? All right.
So are we like redefining the inner product like all the way back to when we redefined it in the beginning? Like
So
is
the inner
now
product-
the definition of the inner product is x
Lebesgue.
equals 0?
So you can imagine that this is to be understood as the Lebesgue integral, but we're going to write it as a Riemann integral. Okay, because that's the way we're going to use it. All right. Ooh. Let's see. All right. Now, so I mentioned this in response to this and talking about, this vector space needs to be closed and whatever, but we can ask ourselves, okay, so how do we actually define closure for a vector space? Okay? So if we define closure for a vector space, or completeness, I should say completeness, then we have the following definition. I'll write it over here. A complete space is one in which there exists no Cauchy sequence of elements of the space which tends towards limits outside the space. Okay. Now remember I talked about, if you add two things together, then they need to give you an element of the space. Okay, so that's closure. So completeness is a slightly different idea, and this is basically, it's not really talking about a vector space in particular, it's just talking about a set. Okay? So a set is complete if there exists no Cauchy sequences, the limit of which is an element outside of the space. Let me define a Cauchy sequence for you. So if I take a set of elements, Sn, so n just labels the element. So if we take n to infinity, then we're looking at the limit of the sequence. Everybody remember the difference between sequences and series? Who remembers the difference between sequence and series?
The series is when you add it, the sequence is just the terms.
It's just the terms, yes. Okay, good. You got that? All right. I know, we're hearkening back to ideas way back in the day. Okay. Is such that given a number epsilon greater than 0, there exists, there's some index n, which is a function of this number that you picked epsilon, such that if n and m are larger than n, then the difference in the nth and the nth element has a magnitude which is less than epsilon. Okay? Just look at that for a moment and think about it.
Does the epsilon need to be like a small epsilon, like we've been defining conservatively, or does
It doesn't have to, but you can take it to be very small.
Okay.
Okay, so just just look at that for a moment.
Is n, capital N just like a, oh, it's just an index of there.
Yeah. Okay, are we good? All right. Now I'm going to use this Cauchy sequence, and I'm going to give you an example of an incomplete space. Okay? I am arguing that this space is complete, and I'll tell you why in just a few minutes, but I want to give you an example of an incomplete space. Yeah?
Wait, so what is big N?
What is big N?
Yeah.
Big N is the number that above.
But is it like a function of?
Well, no. So it depends. So the big N depends on what epsilon you're picking. So if you pick epsilon to be very, very small, this big N is going to be very large. If you pick epsilon to be really big, this big N might be 1, or might be 3. Okay? We on board?
Yeah.
Okay. All right, so here we go. So consider X. This is an incomplete space. You guys, you're not laughing. I was writing SI earlier, now I'm writing I. Anyway, fuck it. I'm just going to go. Consider X the space of continuous functions on the interval from 0 to 1 with a norm defined by yes.
Okay.
So X is an element of big X. This way this is space. Okay. Now this is different than our norm, but we can pick different norms. Okay. So the space of continuous functions with this norm, I'm going to argue, is incomplete. Here we go. I am going to define a sequence of continuous functions, okay, which are 0 if t is greater than 0 and less than 1/2 minus 1 over n. It's equal to 1 for t greater than or equal to 1/2. And then it's equal to nt minus n over 2 plus 1 for t between 1/2 minus 1 over n and 1/2. Okay?
Heard about that, like, double, less than, or equals to on both of these, that like it's equal to on both of them, or do they like meet at those?
They meet at this point. Okay?
Okay.
I'll draw the picture just a minute.
Okay.
Okay? So first of all, this is a Cauchy sequence. Because you can show that the difference between two functions just goes as 1 over the magnitude of 1 over n minus 1 over m. Right? And as n and m go to infinity, this thing goes to 0. Okay? So that's one way of identifying it as a Cauchy sequence. But now I want to graph this thing. Okay. So first of all, there's the point t equals 1/2 plays an important role. And what we find is if we're larger than t equals 1/2, then the function just sits at 1. For points below t equals 1/2, well, let's take the second term in this function, x2, okay? Your 0 for 1/2 minus 1/2 is 0. So when t is 0, you're 0. So you start here, and then it's 2t minus 1, or 2, no, oh, okay, so this is just 2t.
Yeah.
Okay? Well, that's a function that does this.
So you defined n as 2?
Yeah, this is for n equals 2. So this is the n equals 2. Okay, obviously the n equals 1 is not well defined because that makes it negative. Okay. N equals 3. Well, it's 0 for up to 1/2 t up to 1/2 minus 1/3. And then it's going to be another constant slope function, such that it again intersects at this point. And I'm not doing these super accurately. I just hope it is fairly intuitive what this is giving us. Okay? So for the various values of the index n, you go along the 0, and then you cross up to this point, and then you go horizontal. These are all continuous functions, right? What's a discontinuous function?
Yeah.
Yeah, it's where there's a break. What does n equals infinity look like?
It's
Goes straight up and down probably.
It's going to be
gotta be a
this,
step function.
Yeah.
and then this. Is that continuous? No.
Step.
So this space is not complete, because there exists a Cauchy sequence of functions, elements of the space, the limit of which is not an element of the space. Now this is an example of an incomplete space, and it hangs critically on the word continuous, because that's what's being violated by the limit as n goes to infinity. That function is not continuous. Okay. If I disregarded that and just said functions, then it would be fine. Okay? Are we good? Now, we have one word that really qualifies, well, two, but we have two words that really qualify what functions are allowed in here, and they are square integrable, SI. And it turns out, fortunately, and this is not provable, I mean it's been proven, but it's way beyond what we're going to do. It turns out that owing to Riesz and Fischer,
What year?
Point Fisher must
I don't know.
I want to know how long it took.
You're really gonna Google?
Yes.
Let the function sequence f1x, f2x be a sequence. If the limit as n and m goes to infinity of fn minus fm squared which is defined as the limit and of m and m going to infinity of the integral from a to b of f n x minus f n x quantity squared dx equals 0, then there exists a square Lebesgue integrable function f of x to which f n x converges. Okay? So we basically have a Cauchy sequence in a square integrable space, and we're arguing that the limit of any Cauchy sequence in that square integrable space, the limit is always square integrable using the Lebesgue integral as your definition of the integral. Okay? This means our space is complete. So we don't have to worry about whether or not this space is complete. It is complete according to the results of this theorem. But there's just a couple of modifying words I need to put in here. Converges in the mean. Next time, we're going to talk about what in the mean in terms of convergence means. And more on that on Thursday. Remember, your quiz is going to be next Thursday, not this Thursday. Okay, I will be rolling out homework assignments as we go, although it's going to be rather hard to give you homework assignments based on this material because it's all this introductory stuff, but I'll see what I can do. All right. That is all.
Thanks, Alex.
You're welcome.